Good morning, you guys. Welcome to Northern Lesson. I'm hoping to carry these on during our self-isolation. What we are looking to try and do is to get you to continue on with studying your Year 12 and Year 13 stuff in the hope that when we come back in September, we just pick up and carry on running. Now, I know some of the practicals are not going to be possible in this, so I'm going to pick some of the topics that are going to be more heavily chemistry-based or knowledge-based, and carrying on with this topic suits that idea perfectly. Now, what we're going to have a look at is something called trends in lattice enthalpies. We are looking at how some of these ionic lattice enthalpies have some covalent nature to them. Now, that means that some of these tend to not be perfect ionic models, and there tends to be a bit of a distortion about the properties of them. What I've got here is, this was an example of a typical Born-Haber cycle. As you can see, we start off on this section here, which is the metals in their standard, metal and non-metal in their standard state. We are atomizing to turn the solid magnesium into gaseous magnesium. Then we atomize the bromine into bromine gas. Now, it says here 2 times the atomization. If you recall, when we did this in notes, we said that the atomization was from 1/2 bromine 2 to Br gaseous. Okay, so we're looking for a single atom. But in this case, because we are using 2 atoms, in order to balance the equation, that's why we've got 2 times the atomization. And then that process carries on around. Now, what we are looking for is the lattice enthalpy here. Okay, so this is the lattice enthalpy of formation, which, if you remember by definition, is the formation of a lattice from its gaseous ions. Okay, so it's got to be Mg2 plus 2Br minus going to make MgBr2 solid. Now, that's the lattice enthalpy of formation. It has to be defined during this process. It can't be done. It's quite difficult to do experimentally. The notes at the top of the page. It can be done experimentally, but it's hard to do theoretically. There is notes at the top of the page explaining how it can be done theoretically, but if anyone's capable of doing the maths at this point, please send me your degree in mathematics, because I have absolutely no idea what that formula means other than at our level. So what I'm actually going to do is go back to the web page in this case, and this is from ChemRevise website. It's the thermodynamics revision topic on this, and what it's going through is it's telling us some of the properties of the ions and how they affect the lattice enthalpy. So for a lattice to be formed, the positive and negative charges have to attract each other electrostatically. Now, the size of the ion and the charge on the ion affect how strongly they attract the neighbouring ion. The larger the ion, the more spread out the charge is, so the less negative the enthalpy of formation will be. Okay, the smaller the ion, the more tightly packed it can be, the greater the negativity of that enthalpy. Okay, so that's the size of the ion. The charge on the ion states that the greater the charge, the greater the attraction to the opposite charge, so therefore the greater the enthalpy, which in this case needs to be a large negative number. So you can see on this little panel here that if I've got sodium and fluorine, sodium's a small atom, fluorine is a very electronegative atom. They have lattice enthalpies between -700 and -1000, so those are quite small negative values because of the interaction between the two. Now in this case, the step from this to this one is the larger the positive atom, the less negative it is, and this is the bit we need to understand, and it's the less negative it is. So even though this looks small and negative number, this is actually, as the factor that's affecting this is it's a +2 charge. So that's the difference really between a +1 and a +2. Because I know chlorine's larger than fluorine, but we're going up into this range here. You can see here with the -2 charge, the value is much, much larger. Okay, so you're getting the idea here that the two negative charges and the two positive charges are more strongly attracted towards each other. In this case, you wouldn't expect that bit of a jump there. What it's then going on to turn round here is to talk about the trends, and it says the trends towards a covalent nature. So I'll look at that, I'll skip that and come back to that and say, what perfect ionic model. If the theoretical lattice enthalpy is the same as the practical lattice enthalpy, then we say it has perfect ionic. Perfect is 100% ionic, and the orbit of the outside electrons here, as you can see, 100% ionic. They are spherical. If the value of the theoretical compared to the experimental lattice enthalpy deviates from that, then we tend to then say that one of the orbits becomes distorted. And in this case, this is where you can see that the negative charge has become distorted, and some more of the electric charge will move towards it, and this tends to be then more of a covalent bond in nature. Okay, so this is saying that basically what we've been looking at as covalent bonds and ionic bonds, there now tends to be this area in between where you can have some features that are both covalent and ionic at the same time, and there's a little bit of time, although it's not that much. So that's what this is looking at. Now if I go back to this, remember theoretical is calculated using an awful equation, experiment was using the Board-Haber cycle. What I've done here is I've gone back to this idea. It says positive ion are small and highly charged and are very good at distorting and polarizing negative ions. So this is a small sodium ion. This is a small fluorine ion. Now because they are both small and chlorine is so electronegative, they both hold their shape as being roughly spherical. If I then take a statistic which here says negative ions or anions that are large or highly charged are more easily distorted. So if I take this up to a chlorine ion, there's a little bit of distortion here. So instead of it being spherical, the electrons get pulled ever so slightly towards the positively charged ion. So this means some of the charge gets ever so slightly distorted away. So the theoretical value will be different from the experimental value. Okay, now the degree to which that happens explains how much of a covalent nature it is. If it is if it's very, very close, then we say it's perfectly ionic. If there's a reasonably large value of it, then we can start to say it's slightly covalent. Now I'm going to slightly move my pad up on this. I do apologise for the movement. So if you're looking at this table here, what we've got is this table is going through and saying, right, this is the experimental value that's calculated from the Born-Haber cycle. This is the theoretical version that's used from this equation. Now, if we subtract one from the other, we get the difference in kilojoules per mole as being 5 kilojoules per mole. If we go 5 divided by 771, we see that that is a 0.6% difference between the theoretical and the experimental. That is a very small, so we can say that is almost perfectly ionic. Lithium, which is, as we know, is smaller than sodium because it's in the shell above. You can see here it's got a larger negative value, which is supporting this positive ion. The smaller positive ions, the greater the distorting effect, and therefore, the greater the pull on it, so therefore the value tends to be higher. So less negative, because this sodium is larger than the lithium, so these values are slightly larger. However, if you look at these two and you look at the difference between it, because it's smaller and we've got the same size atom, you can start to see now that there's a little bit of a distortion. So this is only, instead of being spherical, it's 1.5%, which would be probably next to negligible distortion towards the positive ion. So we could say this is really, really close to being almost perfect ionic. Okay, so there's a very, very small movement of the chlorine atoms, chlorine's electrons towards the sodium, so it would be distorted ever so slightly. So if we're going to draw this, imagine you doing a sphere here like this, the electrons would be just ever so slightly on that darker line, so they move towards it. So there's no really big deal. Lithium iodide with the iodine, it's a negative ion, so the larger, more easily it's distorted. As you can see here, larger ion values have dropped down now. Okay, so this is the highest, that's this one, that's this one. Got small electrons, small positive charged ion, much larger negative ion. Difference between these two values is 16, so 16 divided by 7.4, 2.2%. Okay, so it's still very ionic, with a little bit more covalent nature. When we then go to silver chloride, you can start to see then where this effect is happening. I'm going back to this diagram is happening. We've got a big charge distortion, so instead of it being spherical, it's very much in this shape. And that's because the difference between the experimental value and the theoretical value is very, very large. It's about 135, which is about 15%. So this very much has a lot of covalent nature to the ionic bond. You can see then aluminium oxide is another one with quite a substantial negative charge. Okay, so I'm showing you that. Okay, so it says here, overall, you can work these out and they're quite simple and straightforward. So it says, note, the magnitude of the lattice enthalpy indicates the average strength of the ionic bond. So the larger the volume, the stronger the ionic bond. And then the difference between the experimental and theoretical values tells us the amount of covalent nature is. So strongest ionic bonds have the biggest magnitude. So these are quite strong ionic bonds. Okay, aluminium and oxygen. This is a 3 plus, this is a 2 plus, this is a 3 plus, this is a 2 minus, sorry, 3 plus 2 minus, and 3 plus, sorry, 2 plus 2 minus. So magnesium would have the strongest ionic bond ionic nature because it's got a big positive charge. And if you check, magnesium and aluminium are in the same group, so actually radius-wise, aluminium would be ever so slightly smaller. Because remember, as you go across a period, the volume gets smaller, the radius gets smaller. This also has a much larger covalent nature to it. Okay, in this case, comparing these two values, we'd have to look at the value here. So aluminium, this has a much larger ionic, strongest ionic bonding. However, this one here has a much larger value than this one for the distortion, so we need to put theoretical on this value from there. Turning over the page, I wanted to have a go at questions on this. When I'm actually going through this, one of the key things I want you to actually do is think about highlighting the information. Now, as I'm going through this, I am straight away seeing that all of these values are negative. So therefore, it's exothermic. If you go back to your GCSEs, exothermic is always bond making. So when you look at this question, it says, are these values dissociation, which is bond breaking, or formation, which is bond making? You're getting an idea. It says then, which of these is the strongest ionic bonding? That's just looking at the physical values and working out which one is the strongest. Which of the compounds has the most covalent? This is then where you have to do that calculation, where you take the theoretical away from the experimental and work out as a percentage. Once you've done that, you can then have a go through the other questions on there. I am available on email. Any time that you wish to contact me, please email me and set work. What I'm expecting you to do is complete through task 6. It then turns over and goes on to enthalpy, which I will set another video up for that one as we go along. Please remember that when you go back, you can also have a look at the notes which are on this page. So notes that on this page, on this document, which is chemrevised.files.wordpress.com, and you will find it under topic 1.8 revision guide, which is thermodynamics.